Okay, so yeah, I'll get started in a minute, but hopefully you guys might have seen that Juliet posted in the post your answers page a perfect example of what the output should look like after having gone through the steps that Paul was showing in order to kind of get that climate pyroxene onset of crystallization correctly without that oversaturation of climate pyroxene. And then also the Activity 6 notebook and the Alpha Melts files have detailed README files. So in addition to the recording for this, if you weren't able to follow along, in addition to the recording, using those files and the documentation on them, you might be able to like recreate that at a later date. And obviously, as I said, I'm going to be setting up some office hours in the future where I can try and help people with this kind of stuff as well. Although primarily my office hours are going to be mostly for PetThermoTools stuff, but I can try and help with other things as far as I can. Okay. All right, so hopefully everyone has been able to open up activity 3. Okay, so this is going to take us through probably the next hour to an hour and a half maximum, and then we're going to actually hear a bit more about MageMin from the developer of MageMin and how you can run MageMin through Julia without having to do it through PetThermoTools. It will be quicker, and the disadvantage is you can't interact it with Python code as easily. You can't compare it to melts as easily, but it will definitely be quicker if you don't have the overhead of trying to initialize those Julia pieces. So we'll hear a bit Nicholas Reel about MageMin and the advantages you might have in running it through their Julia interface or through their app, which is also you need to have Julia in order to install their app. But that's something we'll do from around 11 onwards. Until then, we're going to see how far through this notebook we can get. And it's going to be the same as yesterday. I'm going to kind of go through what I want you guys to do. I'm going to wait for people to post their answers. I'm going to ask people to, if they have issues, to post it in the Discord chat. And we're going to hopefully get through most of this. It should be a bit smoother than yesterday. I'm going to start with like one little tip I would suggest that I came up with yesterday for checking some things, because I believe one of the issues that a few people were having yesterday is they were running the calculation and the alpha melts files weren't on the Python path properly. And PetThermoTools, and this is something I'm going to try and fix, didn't recognize that. And so just waited for the timeout to be hit. And so it was waiting for the timeout to happen continuously. It was taking like 40 minutes or something for those
Matt,
timeouts.
you're a bit quiet. Are you using a microphone?
I will switch back over. I can't use the microphone and keep my charger in, but I will switch.
Sounds like a Mac issue.
Yeah, it is. Okay, is that louder?
Not really. So is that loud if you, I mean, it's fine with headphones on, but it's very quiet without.
Okay, one sec. If I stop my share, I can
Oh, that is a
adjust.
bit, what do people think? Is that louder? I think
Is this
that is
okay?
louder. Yeah,
Better. That's better.
that's better.
Okay,
Yeah.
awesome. Thanks. Okay, so yes. Yeah, so what I was saying, one of the things that seemed to be a problem yesterday is people were like running the calculations, and ultimately, like under the hood, PetThermoTools wasn't able to find the alpha melts files. And so from that, basically what it meant is that it wasn't running any calculations, but we weren't catching that error properly. And it meant everything was just waiting for the timeout, then returning nothing, then waiting for the next timeout and returning nothing. So for some of you guys, it was sometimes taking 40 minutes to return nothing, which is not ideal and definitely not what I want to do in this case. So what we're going to do for this one, firstly, for some of this notebook, you're going to need firmware. So if you do not have firmware installed yet, please run this first self pip install firmware and then restart your kernel. I'm not going to do it because I already have the most up-to-date version of firmware on this computer. We're then going to run this. We're going to import all the different Python packages we need for today. Remember, if you are running PetThermoTools and your alpha melts files are not on the Python path, you need to add them in here. So path to alpha melts for Python in there. Okay, so you need to add those two lines of sys, import sys.path append, and then whatever that path to those alpha melts or Python files we were using yesterday are, you need to add that relative path in there to make sure they're located. Okay. For everyone else that was able to do this without doing that, you can just run this cell without adding the import sys. But regardless of which way you do it, What I would then suggest doing is running this second cell down here. And this isn't actually in your notebook, so you're going to have to make a new cell. So there should be a plus code button, whether you're in Jupyter Lab or in Visual Studio Code, a plus or a plus code button. Add a new cell, and then run this line from melts dynamic, import melts dynamic. Okay. And this line, if the alpha melts files are on the path, should just work perfectly. If I restart my kernel, and I can quickly try and show what would happen if. Don't do this, by the
Yeah,
way.
don't do this.
Don't do that. This is me showing what will happen if. It's like if I restart the kernel. Yeah, so if your alpha melts files aren't on the Python path, you'll get error no module name melts dynamic, and that means you need to use either you need to reinstall the install alpha melts function, or you need to run the sys.path.append line. Again, it maybe there's something wrong in it, if that makes sense. But this is how you can check are the alpha melts files like readable from PetThermoTools. Okay, so I'm going to quickly fix the fact that I just broke my installation. There we go. Right. And now, so yeah, you don't need to do that. You should be able to start from here. It should locate the alpha melts files, and this should run with no issue. And as long as that runs with no issue, then we're good to do the rest of the notebook. Okay. Once again, because I'm on Mac, I'm going to run this cell twice to suppress those outputs. And then we're going to move down into the rest of this. And so what we're going to do in this notebook is we're going to do some magma decompression stuff. So we're going to track magma from depth within the crust. We're going to allow it to ascend towards the surface. And really what we're going to focus on is the kind of like the fluid chemistry and the fluid mass and kind of volume proportions during that decompression step. So we're going to start using some data from Kilaware. This is actually some of Penny's melt inclusion data. So in this in this Excel file, kilaware.xlsx, there is a sheet named olivine. These are olivine hosted melt inclusions. As Penny has just said, if you have issues with thermobart installation, potentially some conflicts with other packages, don't worry. You don't need it for the entire notebook. So you can still follow along the majority of things. So we're going to import Kilaware. Once again, I'm just filling anything that was a nan with zeros. It's going to help with just a couple of steps later on in the notebook. And this .head function will show you the first 5 lines. So you can see, as before, we have our chemical data. Because we're following these thermobar naming conventions, we have underscore liquid to indicate that these are liquid compositions, and then underscore ol to indicate that these are olivine compositions. Okay. We're also going to load in this data from Mount St. Helens. And this is actually data from John Blundy and Kathy Cashman's work in 2025 from the white pumice of the 1980 eruption. So we're going to load this in, and you can look at the data again. And the type here is indicating the type of melt inclusion. So I believe A1 indicates amphibole inclusion. I believe there's also plagioclase inclusions in here. What we could do if we wanted to investigate this, right, because you're all experts with pandas now, you can do St. Helens type dot unique. Okay, this will take all the unique values in this type column in here. And so yeah, amphibole inclusion, plagioclase inclusion, and ground mass. Okay, so here we have 3 different types of glass measurements from the 1980 white pumice that we're loading in here. As we move down, if you've successfully managed to import these 2 cells, you should now be able to run this code. So this is how I set up plots. It's slightly different to how Penny sets up plots, as we discussed yesterday. But you should just be able to basically plot the Kilaware silica against sodium plus potassium, the St. Helens silica against sodium plus potassium. I'm just doing this in a basic matplotlib subplot rather than using Pyrolite. You could use Pyrolite quite easily here in order to get the lines drawn for the full TAS diagram. At this point, I haven't gone around to actually doing that in this case. Okay, so I just want to quickly stop there and make sure we pause there, make sure everyone has managed to get the files imported and managed to get that plot working and looking like this. And this is just a kind of first check to make sure everyone's kind of keeping up with, we've got everyone following along, and you all have the data ready, which is kind of what we're hoping for. So yeah, give me a thumbs up in the chat. Is that a raised hand, Dawn, or is it a I'm successfully?
I just had a quick, can you just briefly go over the extra code for the install again? With because I tried the from melts dynamic import and it came back, but like I don't think I need it, but I just want to understand the logic just one more time.
So yeah, so this is basically the melts dynamic file, which actually I could open up briefly. This is basically where a lot of Paula's magic happens. And so this is like the underlying file that really runs alpha melts or Python, essentially. And so we're just trying to basically say, can we import this class from this file? And the idea is that if your installation has worked correctly, you should be able to import melts dynamic. It's just basically importing one class from this file here. And the key thing is that tells us this file is on the Python path. If this returns an error, it means no PetThermoTools calculations are going to run. And so if that returns an error, it means that either this file doesn't exist anywhere on your computer, or alternatively, you need to import sys.path_append and make sure you have the correct path in here to find that file.
Right. Okay.
So if you're getting an error with melts dynamic, import melts dynamic, just make sure your import sys.path_append is exactly the same as what you had on yesterday's notebooks to make sure it should work correctly for this. So I'm going to go back to the first notebook we did quickly because Penny actually does it this way. I don't. So you can see on Penny's, this is like the location of her. She quite cleverly has a melt installation folder, which has the alpha melts files within them. And you're looking for, on Mac, it will be Mac OS, I believe, rather than Win 64. But you're basically looking for the location of this folder. And you need to point Python towards that folder. And it should contain your melts dynamic.py file and the other alpha melts.python files. But yeah, basically this step here is we're not actually going to use melts dynamic within this environment, within this process. It's just a check of, are these files on the Python path? If this works and doesn't return an error, then we're good to go. If it returns an error, then you need to come back up here and make sure the sys.path_append path is correct. Hopefully that makes sense.
Yes.
Cool, awesome. All right, so hopefully, Penny's put another way to get the line to the task plot up as well. If people want to try having a go at that. So I think I saw a few people put thumbs up and stuff. So if anyone is having issues, post in the Discord chat or unmute and ask now. We want to make sure we don't let anyone fall behind at this stage, essentially.
I think we're good, Matt.
Awesome. Okay. So what we're going to do is we're actually going to start subsampling some of the data. So within the Kilauea data set, if we scroll back up, you'll see this label parameter. And I think, Penny, do you want to explain what these labels represent briefly?
Yeah, and you can type to Dawn what she needs to type because she's missing a word. Yeah, so this eruption was the 2018 eruption. It represented things erupting from basalts, which is what we'd expect at Kilauea, all the way through to andesites and dacites. So these sample codes represent different fissures, so fissure 4, fissure 8, fissure 13, fissure 17, etc. What Matt's going to do here is just grab the fissure 8 samples, which have the sample code LL8. They are your nice basalts that represent the main phase of the eruption. So we're going to be doing those. We could also do, and in the paper I did, this was actually using melts for MATLAB before the Python thing really existed. We also look at the more silicic ones, and we use that to look at differences in explosivity between dacites and basalts. But for now, we'll do the basalts, and we're going to compare it to melts and helens instead, for those of you who like real silicic volcanism rather than Hawaiian silicic volcanism.
Yeah, once again, these things are often adapted from things I've developed for teaching undergrad petrology classes. And so doing a comparison of basalts to higher silica magmas is something that I've done in that case. So we'll look at like viscosity of the magmas and things like that later on. But what I'm just doing here is adding, so like you can see initially in the initial kiloware data set that Penny did, she managed to find 154 olivine hosted melt inclusions. This is far better than the 9 olivine hosted melt inclusions I found during my PhD in my system. We're going to subsample it. So I'm looking into the label, and this is slightly different to what we did yesterday. But when you have a series of all strings, so all letters, you can hit this dot string dot contains, and it will search for any value within here that contains LL8. So it doesn't have to have that as the entire string in that row, but as long as it contains that, it will take that out into the new data set. And so if I run that and then run length F8, which is a new data frame I'm setting up here, you can see that we originally went from 154 rows to almost 50 rows for Fisher 8. And so you can see that in this case, it was almost a third of Penny's data set was from Fisher 8. Okay. We're also going to do this next row here. So what we're doing in here, if I take this out separately, is in Fisher 8, one of the columns in here, Penny's head's in the way, is P bars. Okay. And if we're doing a decompression calculation, we kind of want to find ourselves a starting point. And you could argue that maybe with melt inclusion data, that maybe starting for the system that had the highest pressure, potentially the least influenced by degassing or post-entrapment processes that could cause loss of volatiles, maybe that one with the highest pressure might represent something approaching like the system prior to decompression. Maybe taking just the highest one is maybe a little bit too much, but nevertheless, we can kind of use that as a starting point for our decompression calculation. So what I'm asking here is I'm asking it to give me a statement of where in this P bars series it is equal to the maximum value of that series, right? So most things are going to be false, and there should be one true. So row 18, index 17 here is true. Everything else is false. Unless you had two values that are absolutely identical, that's what you should expect to see in this case. And I'm just saying here, so locate the rows where that is true. I don't actually need the comma colon here, but that's just saying and give me all the columns as well. And this dot squeeze is, I can't remember exactly why that was necessary. Let's try it without. Oh yeah, so the dot squeeze converts it into a pandas series. Sorry. So when I load this into the decompression calculation, because I only am giving it one composition, I want to give it either a dictionary or a pandas series. If I give it a data frame, which is what is currently shown here, it will assume there are multiple calculations, which there aren't, there's only one. So the dot squeeze, it just converts it into a pandas series instead. And this is the composition we can load into PetThermoTools in order to run a decompression calculation. And so this is, well, the calculation we're going to use, okay? And ultimately, this actually runs the exact same function as the isobaric crystallization function that we ran yesterday. There is a function in PetThermoTools called multipath. And basically what isothermal decompression does is it calls multipath and it just tells it to change pressure. Isobaric crystallization calls multipath and tells it to change temperature. They're actually almost identical functions. It's just what information we're sending there that actually changes slightly. So in here, we could see very similar things. We have our model. Once again, we're doing decompression for a system that contains water and CO2. So we should use the MELT 1.2.0 model. This is the more recent rhyolite melts with the mixed solubility model. We called this parameter here Fisher 8 start. So that's going to be our starting composition, okay, our bulk. We want to start at the liquidus, and we are going to buffer it at FMQ to start with, okay. We're going to start at quite a high pressure, actually at the pressure determined by this sample, okay, so that's where I got that pressure from. We're going to end at only 50 bars, so very close to the surface, and we're going to move in 20 bar increments as we move up towards the surface, okay. There are other parameters you could put in here. If you are getting nothing returns, use the timeout and increase that up to something like 180.
For a single calculation, the default timeout, I believe, is set at 180 already for this, and it should be fine. You could, once again, start to think about things like fractionate fluids. Okay. Without that parameter in there, I'm going to keep it, not have that parameter in there for now. It's going to keep everything in the system together. So as you move towards the surface, it's going to keep the fluids in the system. It's not going to allow any of those fluids to escape. And any solids that form, same, it's going to keep them in the system.
And this would be in other degassing programs, this would be your open versus your closed system degassing. So your closed system would be keeping everything in the system. Your open system would be allowing that fluid to fractionate.
And so hopefully people have been able to run that. And what you should see, hopefully it should only take a few seconds. If your system's struggling with Zoom running at the same time, maybe hopefully only up to like half a minute, I would expect. It shouldn't be too much more. Hopefully you're able to run that. And what I want people to just do quickly is, if so, have a look at the output. So just like we were doing yesterday, this kit-aware decompress, we can do .keys, and it will show us the different kind of data frames which are included in that output dictionary. And you should notice that it's essentially exactly the same as what we had yesterday for the crystallization calculations, right? We have a conditions data frame. We have a data frame for the phases that saturated, so liquid and fluid in this case. We have a data frame for their properties. And we have separate data frames of things such as the mass of the system and the volume of the system components at different points. So we could do that. We could look at the volume of the system. And you see that we start entirely at liquid and actually immediately saturate in some fluids. And this is not surprising, seeing as this is the pressure determined by melt inclusion saturation calculations. I can't remember for these pressures, if these are magma sat pressures, Penny.
Okay, they are indeed magma sat pressures, so they will be internally consistent with melts. The only difference would be I would have used a liquid thermometer, whereas you've used the melts liquidus, but it won't be that different.
Yes, as we saw yesterday when we plotted up the melt inclusions against each other and did the pressure plot. See if I can find it quickly here. The only difference is, and we're in this like very low pressure region down here. Basically, I'm using the melt temperature, and the pressure in Penny's data frame is using an empirical thermometer. So there might be a slight offset, which is maybe why it didn't start fluid saturated, but it's essentially very close to fluid saturation because it's an internally consistent solubility model. So hopefully people have managed to run the calculation. Can people give a quick thumbs up if that is the case? I don't think I can actually see the thumbs whilst I'm in. Okay, awesome. You're going to have to let me know because I can't see the thumbs when I'm...
Tons of thumbs. We're good.
Ideal. And so, yeah, the key thing here that I wanted to emphasize is the output is the same, right? The output is the same regardless of whether you're doing decompression or crystallization. You can kind of treat it in the same way. One of the only ones that is a little bit different is the fluid. We didn't look at the fluid yesterday at any point. The fluid in melts is only water CO2. And so I've kind of just cut out everything else that would be in here. Like every other phase, you get something for silica, titanium, aluminum, etc. For fluid, I'm only going to give you the water and the CO2. And the other thing what we've calculated for you is the mole fraction of these two components in the fluid. Okay, so you can see that first step, no fluid was saturated. The second step, our mole fraction is around 95% CO2. And another thing you can do in pandas is look at the tail. And here you can see that actually by the final step of the calculation, we're almost at 70% water in the fluid composition. Okay, so we can do that again. I'm just going to run through these cells as these are essentially just repeating what we have above. But what I would like people to do in here, okay, is I would like people to, this is two different subplots. So A0 would be the one on the left, A1 is the one on the right. I would like people to have a go using that output structure at plotting the fluid composition. So let's start with maybe the mole fraction of water. If you want, add a second line with a different dash type for the mole fraction of CO2 into this plot, this first plot. And in the second plot, plot the volume fraction of the fluid. Now you're gonna have to do a little calculation for this because if we have the volume parameters here. I'll just do dot head to show you the first bit. We have two parameters, right? So I want you to show the volume fraction. So you're going to have to calculate the fraction of the system, which is fluid relative to the total volume of the system. Okay. So have a go doing that. See if you can at least see if you can get this first plot running, and then see if you can get a kind of volume fraction calculation going based on this information as well. Okay, so give everyone like 5 minutes to do that. And if you have any questions or issues, post them in the Discord chat, or feel free to unmute yourself as well and ask questions as well. There was a question on Discord about pH melts through PetThermoTools. That is not currently possible. Paula can potentially answer better than I can on that. So pH melts is the version of melts that allows some water to fit into non-mineral anhydrous minerals, which can be very useful for kind of decompression melting calculations, especially.
Yeah, I'm just typing that, yeah, no, reverse crystallization and pH melts are not currently available through PTT. That we're working on moving those over from Alpha Melts 1.9. And I was about to write, and will, for the record, finish writing, that, you know, if Mariana or anyone else has examples that they want to run using those functions and would like to be involved, then, you know, that will allow us to implement this sooner, you know, if we have people that are willing to test it out while it's, you know, in development. So, yeah.
Yep. Awesome. Thanks, Paula.
Reach out if you have a thing that you want implemented soon.
Thanks. Awesome. So you can see, those of you that are currently doing this, you can see Penny has put in a example plot for the water mole fraction and the fluid volume fraction as well. Are you showing the volume fraction, Penny, or are you showing the just total volume, the volume fraction?
I'm showing the volume fraction, Matt, because that's what you
Okay.
told us to do. Is
Fair.
that not what yours looks like?
No, I would just argue it's more of a volume percentage, to be honest.
It is a volume percentage, but you're the one that labeled the axes.
No,
Hold
I
on,
know,
volume
I know.
percentage. There we go.
So I'll start by showing, hopefully everyone's still working that, or a few people have managed to get things working. If you have managed to get it working, put things into the post your answers chat so we know when people are finished and getting the correct answers. It'll be really helpful. It's really helpful for us to make sure everyone's kind of keeping up and staying along with the workflow.
If anyone needs help, send a message help in the ask for help, and I'll jump in a breakout room with you.
So I've just put in the first bit to hopefully get people started. Nice. Alex has also just got the first bit working, nicely showing the offset and comparison of water and CO2 mole fractions in the plot. So that's what you're aiming to get to, essentially, is what Alex has shown up there. And really, to do this, you're going to draw up two things. Our x-axis, we want to draw from that fluid data frame. Our y-axis, we want to draw from the conditions data frame where we have the pressure information. You can also do this both from all as well. I prefer to do it from their separate data frames because it keeps some like structure to where I'm kind of putting the information from. For me, that's more logical, but you can do it from all as well if that's easier for you. Nice, yeah.
Lichen. I think we'll move on once 5 more people post. Just so please keep posting, folks. It's the only way we have any idea of whether we are going too fast for anyone. And again, we can hop in a breakout room if you can't work out how to get there.
And if you've just like not got the calculations run as well, please let us know, like so we can try and figure out what's gone wrong in that sense. As a couple of people have posted that, I'll show how I would code that up.
Matt, just give people another minute.
Yep.
Yay, go Juliet.
Nice. Nicely done.
Except, yeah, she's done XCO2. Nice.
Mm-hmm.
I was thinking, no, it's the wrong way, but it's the right way for CO2.
Obviously, if anyone's really interested in sulfur degassing, that's not currently, I don't know if there's any plans to incorporate that in the three-way solubility model into melts. So in terms of actually incorporating SO2, there are ways you could try and like take the outputs from melts in terms of the water and CO2 mole fraction to try and then feed in to other sulfur degassing models in order to calculate that externally. It's not something I have built into PetThermoTools, but it is definitely possible using some other tools to try and like look at sulfur degassing as a kind of add-on step in this as well. Yeah, Julia, did you do fluid divided by liquid maybe rather than fluid divided by the sum of two?
Dawn, you've got your hand up.
Yeah, I'll go check what it is.
Yeah, so I just want to make sure I understand your use of fluid one and conditions. You're using those because this is a dictionary and not just an Excel file equivalent. Is that correct?
Yeah, so if I had just run decompress, it's a huge structure. So like there's a dictionary called conditions, a dictionary
Right.
called a data frame called conditions, data frame called liquid.
Right.
You can, if you just want to simplify it, just use the all thing, the all data frame, and this is a data frame that basically copies everything in. So we have p bar, so you could get the p bar variable from all. You should be able to get yeah, you can get the mole fraction of water in the fluid as well from all, and it's the same column headers as what you get in the individual data frames.
Okay.
So it is possible just to use the all data frame and everything's there. I personally prefer using the individual data frames because for me it just like helps my brain figure out where things are a little bit better.
Sure, but I'm just trying to understand, like, for people moving from like Excel space, like you having that the all point, like the fluid pointer or the condition pointer is effectively like the sheet's name.
Yeah, so if we go back into this is the output I exported from one of the calculations yesterday. Hopefully you guys can see this. And so this is I exported this from one of the crystallization calculations. But you can essentially think of the overall results output as the entire Excel workbook, and then each individual item within the dictionary is its own sheet within Excel. So in here, one of the sheets in this Excel notebook would be all, and this would be this one that's this big combination, including everything that formed during the crystallization calculation. Whereas every other sheet will be the kind of like individual parameter at that step, essentially.
Awesome.
If that makes sense. Good. Nice, Lynn. That looks good. Yeah, we're getting a few more graphs coming through, which is excellent. So yes, so this is the code I'm using in order to plot. I'll also, in this plot above, just show how I would calculate if I was doing volume fraction. Okay. So there's actually a couple of ways in order to do this. If you want decompress, you can look up the volume of fluid like that. And then you could divide this by and kill away a decompress all. There is a single volume term here. So you just phi underscore centimeters to the power of v to the power of 3. That's the entire volume of the system. Similarly, if you went all here and then did the, see if we can autofill, you can see here there's also volume underscore fluid, volume underscore liquid. Okay. So you could use this volume underscore fluid here, and that would give you the, for every row, the volume of the fluid divided by the volume of the entire system in this case. Okay.
And you can also define this, the way I defined this was fluid over fluid plus liquid as well, depending on exactly. I mean, if you're fractionally crystallizing, it's not really going to make any difference because the amount of solids is minimal.
Yes.
Where that will differ is if you're doing equilibrium, or I guess if we're keeping crystals around versus not keeping crystals around.
Yes. Yeah, so there are a few ways to do this. They should all essentially return more or less the same
Particularly
answer.
for this system where there's not a lot of crystals forming.
And so in terms of actually plotting this up, as more and more people are starting to show their plots, which is excellent, so I'll show what I would do, is instead of this mole fraction parameter here, I would just include the volume fraction I defined above. So that's this ratio of the fluid volume fraction to the total volume of the system. Once again, plot that against the pressure of the system. And so the curve should look something like this. It ends up around 30% of the system is a fluid, in this case, in terms of volume, rather than the, if it's mass, it's obviously much lower, but in terms of a volume, you end up with around 30%. So I'm just going to leave these lines of code here and let everyone see if they can get the second plot working as well. While I'm doing that, the first plot looks excellent. Nice, yeah, so looking good, guys.
And Matt, do you want me to just quickly talk about the comparison we did with the day sites for this, just to show people what you can actually do with this?
Yeah, do you want to share screen or?
Yeah, I'll share screen. I'll
Yeah,
give
so whilst
people
are doing that, actually, I'm going to put a screenshot whilst Penny's doing that. I'm going to put a screenshot of the code I used in Discord so people can still see that whilst Penny takes over.
So I worked on this paper with Paula during my PhD. So basically, at fissure 17 of this eruption, we had a dacite and a basaltic andesite erupting next to each other. And the dacite was showing these amazing like strombolian fountains, and the basalt was showing the normal like Hawaiian, less explosive fire fountaining behavior. So once we had a melt inclusion composition for both, we were able to show that. If you look on this side, the dacite had, Matt, there's an echo. Can you mute, please?
Yep.
The dacite had about 1.7 weight% water, whereas the basalt had less than 1 weight% water. So that meant we were able to model for both the basalt and the dacite how much volume fluid you'd have as a function of pressure. So you've basically run a slightly different basalt model. You've run a slightly more primitive basalt model than the one that erupted at this fissure. But what we could basically see is that the dacite exsolves its fluid much earlier and has a much higher volume % of fluid at a single pressure. And so what we're actually able to do is divide these lines by one another. So basically look at the volume of the fluid in the dacite divided by the volume of fluid in the basalt. And you can see at about 200 bars or about 800 meters depth, you have 8 times more bubbles forming in your dacite, which really allows those gas slugs to form and form those kind of like strombolian explosions. Similarly, we won't show this today, but you can also track viscosity as you ascend, and here we're showing the viscosity of the dacite divided by the viscosity of the basalt as you ascend up towards the surface. And you can see, depending a little bit on what temperature you use, whether you use a melt temperature or an empirical temperature, you get between about 50 and 150 times more viscous. So it's that combination of having more volatile volume and a higher viscosity that really allows those gas slugs to form and you to form those beautiful explosions that we saw at this fissure. I don't know if I've got a picture of them. I think I have a picture of them. So yeah, you can see this is really the contrast we're talking about. This is your explosive dacitic melt, and this is your much less explosive basaltic andesite melt. So again, that took quite a lot of work in MATLAB, but now Matt's done it. You could do that study in about 5 minutes using PetThermoTools.
Yes, I think one of the challenges we used to have the MATLAB version, I honestly don't know if this is still something that happens, Paula, is when trying to run a really large number of calculations, it used to basically crash MATLAB because of a memory issue, I believe. So Penny kept having to come into my office and steal my desktop because I had a high-powered desktop in order to run these calculations, and didn't give me co-authorship for this as a result.
Well, it's just a desktop. I mean,
He kept kicking me out of my office, is what happens. But yeah, now this is another like one of the motivating factors for doing this kind of sub-process parallel processing step, because it gets around this kind of memory issue. I've managed to paste code instead. Gets around this memory issue that used to at least influence some of the melts for MATLAB calculations. Okay.
Yeah, I don't know. I haven't. It's been quite a long time since I tried something that large in MATLAB. Or um, I yeah, I used to have to like just stop and continue. I had a way of like restarting. But I don't think I ever crashed MATLAB that way. I crashed MATLAB other ways, but not by running out of memory. And that was on a much lower spec laptop that I had at the time. So I don't know.
Yeah, I think I definitely pushed it to its extreme at one point, because I was one of the studies I did with the MATLAB version before we moved over to PetThermoTools. I think I had something like 4 melts instances open simultaneously that were all talking to each other to look at like the change in the system by tracking the enthalpy across different components and stuff. And it ended up, I think it was a bit much, full stop. But eventually we managed to get it working. We just had to run it in like smaller parts, but it did work.
Yeah, I never really, other than a very, very quick test, never really tried the parallel processing in MATLAB. I mean, I know it can work, but yeah, I'm sure. I'm not that surprised that you could run out of memory that way and things like that.
Yes, I think I say you overdid it. Okay.
Yeah.
All right, so a couple of questions to think about whilst we kind of move on. And yeah, what are the interesting things to kind of think about? The fluid compositions, we kind of already spoke about this, right? At 1,000 bars, it's dominated by CO2. As we move up towards 100 bars, it's actually pretty much here where the crossover happens. And if we also think about the shape of the fluid volume fraction curve, I describe this as a kind of exponential increase in fluid volume fraction as we move towards the surface. So there's a rapid rise, especially as the onset of like water really contributing significantly to that kind of fluid composition. Around that same point is when we start to see this really rapid rise in the fluid volume fraction in the system. I'm seeing loads of people posting their answers, so I'm going to continue moving on. One thing that I should point out, and I kind of mentioned this yesterday, is when we think about the volume, this is once again assuming that initial system has a mass approximating 100 grams. Okay, these are real units. This is grams, this is centimeters cubed. If you're trying to model a real system, right, and you have some idea of like, let's say your mass of your erupted products, okay, you would just need to scale up these parameters from 100 grams to whatever the kind of like mass of your system you want to simulate would be. And you can do that kind of afterwards. It shouldn't influence the like pure thermodynamic calculations going on here. But just as a heads up that these volume, this is like a real number for 100 grams, essentially. Hopefully that makes sense.
But I think it's just worth saying with that fluid volume fraction, you can see it really is quite low until you start really degassing a lot of water. And that makes sense because this bulk composition only has 0.088 weight% CO2, but 0.5 weight% H2O. So if you were to plot like volume against H2O, you'll see that although like a fluid does degas initially that's very CO2 dominated, it's really your amount of volume is correlating with your amount of water in this system because there just isn't a lot of CO2. That's not always true. There's some nice case studies now showing magmas with 1 to 2 weight percent CO2 erupting, and in that case, the CO2 will dominate the volume. But when you've got a few hundred ppm, like 800 ppm CO2, it's not going to do a huge amount in terms of bubble volume.
All right, so hopefully that worked for everyone. That's just hopefully a nice, simple introduction. We're going to now move on to Mount St. Helens. So look at a very different system. Look at the products from the 1980 eruption of Mount St. Helens. And once again, it's something I kind of designed initially for our undergrad petrology class, where we talk about differences of kind of low silica to high silica magmas. And so obviously, I'm thinking that a lot of people in the call will obviously know what the main differences are between a basalt and a dacite. But regardless, it's kind of interesting to look in terms of the differences that we might expect during degassing in terms of the fluid proportions and also the viscosity of materials. So in here, I'm actually just selecting a composition that's a relatively primitive melt inclusion from this data set. It's one of the plagioclase hosted melt inclusions. It actually has a measured water content of around 6.4 weight percent. So if we run this cell here, that's going to extract this single series from the St. Helens data frame. So once again, we have a series which we can use as our initial composition in further melts calculation models. Okay. And so in here, what we're going to do is we're going to run this calculation. And similarly to what we were doing yesterday, we're now going to add a little bit of complexity. We're going to run the calculation. We're actually going to simulate what would happen if this magma had different water contents. So 2, 4, 6, and 8 weight percent water. And we're once again going to label these results by that initial H2O content. This fluid sat equals true statement we haven't seen before. But what this is going to do, and it would be really important, say, if I had like 20 in here as a fifth option. What it's saying is I want to start the system with no fluid. So we're going to start the system, and if at that starting pressure, the starting temperature, the system has an excess fluid phase, it's going to remove that fluid from the system and start the system at the point of fluid saturation. So fluid sat isn't going to increase the water until fluid saturation. It's actually going to remove excess fluids from the system. Okay, so it might be, I kind of realized the way I kind of named it could be interpreted in two different ways. The way this is working is it's removing excess fluids from the system if your system is fluid saturated.
And again, for those that have run other degassing models, the opposite of this would be what you normally do in other models where you specify a volume of exolved fluids. You'll often see people plot an open system and a closed system path, and then they plot a path that's in equilibrium with 2 volume percent fluid or whatever, because it will change your XH2O and your partitioning into the fluid phase. So Matt's just said, like, it's just the opposite in that you're removing it rather than specifying it, because melts, you can't really specify it in the same way you can with those empirical models.
Yeah. And so the only thing this should all run, the only thing I would encourage people to do is input an FO2 offset. We ran Killaware FMQ, let people decide what they think the FO2 of Mount St. Helens should be. You need to just make sure it's just a single, either a float or an integer variable. So don't provide an array or a list, just a single value. And then once you run that, it should hopefully run through without any issue. And I expect it should take hopefully less than a minute for everyone. Hopefully it shouldn't hit the timeout issues we were finding yesterday. Yeah, have a go running that.
Just to clarify, so far we've only been working with FMQ. You can also specify NNO. So you could, instead of, obviously they are related to one another, but you could also put relative to an NNO buffer as well.
Yes, it will run exactly the same way, just with a slightly different buffer, of course, and the labeling will be NNO plus X, or whatever you put in as the offset. If you were to label by FO2, here we're labeling by H2O, of course. So I'm giving everyone a couple of minutes to do that, and then send a thumbs up once you manage to get the calculation returned. And yeah, Penny, if you can let me know if there are thumbs up coming through.
There are thumbs up. Mine is still running. So
I'll wait for yours to
for
run.
people that have slow computers, like it's all the Mac and big fancy desktop people putting thumbs up. Oh, mine's just finished. Okay.
Okay, so yeah, for me, I don't know exactly what the FA2 for Mount St. Helens should be. It's probably a little bit more oxidized than, I'll make sure I'm on FMQ just to be consistent with everyone else. A little bit more oxidized than an Ocean Island basalt, most likely in this case. I'm going to put it around 1.5 for the FO2 offset. Run this calculation, and importantly here, the kind of constraints we're putting are isothermal, right? Something we haven't spoken about yet, but the temperature during every step will be the same. Whether or not that's kind of the most accurate or realistic is something we can talk about in a bit later, but that's kind of the initial assumption we're going to use with these decompression models. And so just like yesterday, now that we're running multiple calculations, okay, we have multiple keys in our initial data frame. So I think it was Dawn asked about how does this relate into Excel kind of spreadsheets. Each of these files, if you were to save them, would be saved as a different Excel file. Within each Excel file, there would then be all of these different sheets. Okay, so if you want to think of it in terms of Excel workbooks, each system here is a different file. Within each file, there are different sheets in this case. Okay. And one thing we can potentially do is start looking in like a particular one. So we can look at like the one which starts with the most water. And we can see that one actually in this case, unsurprisingly, we only started with 0.025 weight % CO2 in the system. That's specified in our function. So our system is straight away from the start 99.5% water in terms of that fluid fraction in this case. One thing we also could do is we could potentially look at the composition of the liquid phase, okay? And the reason why I'm going to do this is to look at the initial water content of that liquid, okay? So you can see that the water content of the liquid here is 6 weight %. We specified 8 weight % for our inputs, okay? So this tells me that the system must be fluid saturated from the get-go. And actually that 8 weight % was too high. And so we started fluid saturated and the excess fluid phase would have been removed prior to the calculation. So if we go and look in the volume, we should see only a very, very small amount of fluid in that initial step. If we hadn't put fluid sat equals true, we would have likely started with a significant fraction of our system already pre-existing as a fluid at the very first step of the calculation. Okay. And maybe that's not an issue if that's not an issue for you, just delete that line essentially in this calculation. But hopefully that kind of shows a little bit about kind of how you kind of extract this information. So it's the same as before, but we're specifying now which calculation we want to do as we ran multiple calculations. So in this plot, this is going to use something that I don't think we've come across yet in terms of a for loop. Okay. So one thing that is quite useful if you're trying to plot up the results, and this is essentially what's happening in the background, that Harker plot I showed you yesterday. One thing that can be quite useful is using a for loop to loop through the different calculations that you've done. So to show you how this is kind of working, okay, if I were to write this for loop here, I could then, and because I have output suppressed, it hasn't actually worked, annoyingly. But if someone on Windows was to run this, what it would do is it would loop through all of the different keys in Helens Decompress. So the first one will give you H2O 2.0, and on the second loop, it will give you 4.0, third loop 6.0, fourth loop 8.0. So in each loop in here, we're kind of going to extract one of the different kind of results from that overall results dictionary, okay? So this line in here, res equals Helens equals decompress, key. On the first loop through here, res will be equal to Helens H2O 2.0. On the second loop, it will be equal to Helens H2O equals 4.0. On the third loop, Helens H2O equals 6.0. And on the fourth loop, it will extract this final calculation, the 8.0 calculation up here, okay? So in this plot cell here, where we're going to plot the fluid chemistry, maybe just focus on the water fluid proportion for now, rather than plotting from Helen's decompress, H2 equals 2.0 or something like that, you want to plot from res. Okay, so res is going to be on each loop, it's going to change what it is, and it's going to be different. So res, and then you would want to extract fluids, and then from there, you would have to extract, say, the water or the CO2 mole fraction. So if everyone has a go doing that, and as I kind of said here, I'm just focusing on the water mole fraction in this case. So have a go editing this code to see if you can plot the 4 different models, the mole fraction of water in the fluid for the 4 different models against each other using this code, and see if you can add a label to them as well.
I mean, just a hint for those who haven't done a lot of Python plotting before, if you don't specify a line color, it will automatically loop through reasonable line colors. So if you put in this for loop, like a dash and a K, it's going to plot all the lines as Ks. If you just put a dash, it's going to cycle through its default colors for you.
And once again, post the answers into Discord once you got them, and yeah, Penny has posted a little script into Discord of how to save some of these results. So your Stefan, your results didn't complete, so you probably need to set a timeout and increase the timeout maybe to 300 would be my guess. And yeah, and check the melts dynamic, import melts dynamic line ran. If that ran, that means the files are on the Python path. It might just be that you need to increase the timeout. So add a timeout equals 300 in the function above. Because you're I'm just going to quickly grab a drink of water, but yeah, once you've got a plot working, oh, why does pressure go on the x-axis? You're muted.
Because it's the variable you're changing. So
But
it goes on the X.
pressure,
I know that it
pressure
goes down
up
in the
and down.
crust, but the vast majority of plots will be made with
I
pressure
know,
on
I
the
know.
x-axis.
Right, I'll go grab a drink. Back in a sec.
Great job, folks. Lots of good graphs coming through.
What was that, Penny?
Lots of good graphs coming through for people.
Excellent. So yeah, well done, everyone. What we like to see.
What have we got and ask for help? I'm getting the same error still. Ellie, do you wanna hop in a breakout room with me? Anyone that's still getting that emptiness, let's do it. Let's go in. Breakout room. What have we got?
You go breakout room 1.
Breakout room 1.
Yeah, so if you're having issues, maybe jump in breakout room. So label equals key icon is what I would suggest. So res is going to be the entire dictionary. Key is going to be that string that identifies that dictionary, if that makes sense. Oh, Alex has gone fancy and plotted subplots with both water and CO2. Anton has, I think what you're doing, Anton, is you're plotting up the entire fluid. You need to specify a parameter within the fluid. So like the X H2O fluid or something. At the moment you're just plotting, you're probably just copied what I've got here, you're plotting the entire fluid data set. And so for every model, it's trying to plot 4 different lines, essentially. And also make sure you're specifying on the y-axis we're plotting against pressure, I think. Yeah. Looks good, guys. Oh yeah, so as Alex put in like label, you can do F key. Label equals key should also work, I think, at this.
Matt, just FYI, if people leave FO2 offset as ... it doesn't tell them that's not an allowed input. It just runs it till the timeout. So you need to add that as Matt needs to add a catch so that you cannot put things that are not allowed. It
I
should catch them.
don't know how to catch ... What is it counted as a
Well, you would
input?
say it has to be a float or a string and if it's not, then I think you should be able to catch it. I'd be
I
surprised
should
if
be
it's
able
not.
to, but yeah, I'm just curious as to what it counts as. But
Well, I'm sure ChatGPT can tell you.
yeah, thanks for posting the code as well there to help everyone else. So yeah, that's kind of exactly perfect. So like the res fluid 1 x mole xh2o mole fluid, then res conditions p bar label key is exactly what we're kind of looking for. So yeah, really nice work. And then yeah, I'll show you what I'm going to do for this in a second as well. Yeah, so make sure, as Benny just said, this you can't have to remove the ... and add in an FO2 offset into here for these calculations. All right, so yeah, as we've got lots of nice examples coming through, once again, I'm just going to show how I would do this. So that's how to extract the mole fraction of water in the fluid. We then need to specify using the conditions tab that we want to plot against pressure. And then we can specify, let's have a dotted line that's specified using a colon, and then label equals key should work, but the F key should also work. I don't know why some working, some not in this case. And so each loop, what this is doing is each loop, it's going to take one of the calculations we ran. So we ran 4 calculations. It's going to plot the fluid chemistry against pressure. It's going to label it by the name of the calculation. And then it's going to loop through and do that for the second one. And then it's going to loop through and do that for the third one. So res here is just one calculation, but each time it's going to be a different calculation. Okay, so each calculation, we're going to take the fluid. We're going to plot the mole fraction of water in the fluids, and we're going to plot that against the pressure of the system and label it by the name of the calculation. So
Matt, sorry, continue. Can you just do something just so people can see a common problem? For fluid 1, can you delete XH2O mole fluid? So it's just it on line 10. Line 10.
Yeah.
Delete that second thing. So this is what some of you did to start with. It'll plot a complex load of all of the possible columns in that thing. So just if you see like loads and loads and loads of lines, it's probably because you've gone into the dictionary one step, but you need to go one step further to plot the variable that you're looking at.
Yeah, so if you just put res fluid 1, it will plot all 4 columns. I'm muted, aren't I?
No, you're fine.
Okay. It will plot all 4 columns from res fluid 1. So you're looping through 4 results, and each time it's plotting 4 lines. So you'll end up with 16 lines on your curve.
So if you see tons of lines, just go one level down is almost certainly what's happened in that case. I think that's probably what happened to you, Anton, to start with.
Yes, you just want to end up something like that, basically. Then I will just copy that in here so that everyone can see the final thing. All right. Have we mostly had success? If you guys can quickly show a thumbs up for Penny, double check. And as long as we've got at least like good 20, 30 thumbs.
Let's give people 1 more minute.
Okay.
And then
I'll keep this up so people can see the kind of code structure. In general, are we having more success? Are people finding that things are working a bit better today? Are we having less issues? Did having that check for the melts dynamic at the start, did that work? Things like that. If people can just give me a thumbs up if that helped, just like double check things are installed and things like that would be useful. Awesome. Great, thanks a lot, everyone. I'll probably add that until I code in the fix to check within PetThermoTools. I might add it to the examples online. Yeah, exactly. I'll add it to every example online, so that everyone can make sure we don't accidentally miss out on that. Okay, sharing screen again if anyone wants to copy the code.
And then the other thing we'll do is we'll make sure that you cannot feed the function something that will let it run forever. That just involves Matt going through and writing checks for every single input variable so that you cannot give something that's not allowed, and it should catch it before it tries to run to the timeout.
Yeah, so I see a few people have started doing more of the function, which is excellent. So like some people, oh, nice plot, Sue.
Yay, go Sue.
So Lynn, nice plot showing also the CO2 and the water in that sense, which is a really nice way of kind of like showing these two models. And ultimately what this is a kind of maybe a slightly silly calculation because the melt inclusion itself had a measured water content of around 6.4 weight%. But if we were to lower that water content, you could see obviously our decompression starts around 2 kilobars, 2000 bars. The first two models, the 8 and 6 weight% water models are initially fluid saturated. The one with 8 weight% water, although we told it to remove the excess fluid phase, it would have removed some CO2 as well in the excess fluid. So it actually starts almost entirely water from the get-go. The 6 weight% one does have some significant amount of CO2, but actually the 2 weight% water one doesn't start degassing until less than around 800 bars. And when it starts, it has approximately 50-50 mix in terms of mole proportions of CO2 and water in this system down here. Okay.
I think once you can visualize this XH2O, this will really help you like understand magmatic degassing, because I read a lot of papers that say a model is that they think their system is vapor saturated because they're calculating saturation pressures for melt inclusions. And then they talk about the onset of second boiling and the onset of water saturation. Pure water saturation only exists in a pure water system. In the rest of these systems, what you'll see, and you can track XH2O during fractional crystallization as well as degassing in PetThermoTools, is it's not that you suddenly go from CO2 saturated to water saturated. You just progressively get more XH2O rich as you fractionate. So there is no true onset of water saturation. Your vapor is just evolving from being CO2 dominated to water dominated, but it often isn't a progressive switch. It's like this gradual change that we're seeing with this degassing.
Exactly. And so hopefully everyone has got that plot working. And so what we're going to do is now move on to this next step down here. And I will say that you can calculate viscosity using the Giordano method directly in AlphaMelts or Python. I have not implemented this yet. It is something that is on my list of things to do. In the meantime, until I implement it, it's actually very easy to calculate. And so this is something that Paula has implemented in AlphaMelts or Python, but I haven't yet included in the PetThermoTools functions. But if you do want to know the viscosity of your system or the viscosity of the liquid of your system, it is very easy to calculate using Thermobar. So unless if you had issues with the Thermobar calculations earlier on, you should be able to run this line here. So just to clarify, PT is Thermobar, so calculating pressure and temperature, I guess is why it's PT. And PTT is what we typically call PetThermoTools. I appreciate they're quite similar, probably quite easy to confuse, but yeah, P single T, Thermobar, PTT, PetThermoTools. So in Thermobar, there is a function for calculate the viscosity using the Giordano 2008 method. The inputs it requires is a liquid composition, and it requires the liquid composition to have the suffix _liquid. So if we print our liquid composition from the kilowatt data, you can see, make this dot head, let me make that a bit neater. You can see that all of our columns outputted from PetThermoTools have the _liquid. Okay. This means that we can just provide that data frame, so the liquid data frame from the kilowatt decompressed model, we can provide just that data frame to Thermobar, sorry, and it will be able to calculate the viscosity. The other thing we need to provide it with is a temperature. So in our all data frame or in the conditions data frame. Once again, it doesn't matter which. We have a parameter T_C, so temperature in Celsius. The temperature for thermobar is Kelvin. So the only adjustment you need to make here is adding that by 273.15 to convert between Celsius and Kelvin. Okay.
Now, the advantage of having access to thermobar rather than using the melt output itself is we know melt's temperatures are typically too hot. Now, anyone who's ever modeled viscosity knows that temperature is very important for viscosity. So it might be at this point that you want to use the major elements from melts, but you want to use a different thermometer. And that's what I did in this paper, and I'll screenshot that result in the chat. But basically, melts will always give you a lower viscosity because its temperature is too high. So this might be because we're working in, if this was Hawaii, we would want to use the Heltz and Thornberg thermometer, for example, just to get you that more reliable viscosity. Because although the temperature offsets don't really matter when you're working in Melt's world, once this goes into real world and you're comparing to like experiments of rheology, that might be a problem. So you might want to use a different empirical thermometer at this step.
Yeah, so hopefully everyone should be able to run that cell, and it should run, if the kilowatt decompression model worked earlier, it should run without issue. So we can see here our log viscosity of the melt, or viscosity of the melt on the left-hand side over here. And then I believe these are other parameters that are used within the Giordano model calculation. Penny's nodding, awesome. And the temperature in Kelvin that was used during this decompression model. And as you might notice, they are all identical because we ran an isothermal decompression model. So what I want people to do now is to have a go at doing the same for Mount St. Helens. The one thing I will notice is the, if I find, what do we call it? Helens decompress. Okay. Remember that for Kilauea, we only ran one calculation, right? So we can go straight from decompress to liquid. For Helens, we ran multiple calculations. So you first have to specify the composition you want before you can then specify, I want the liquid. Okay. So have a go using, so Penny's just copied it into the chat, her comparison of viscosity using different temperatures, but have a go calculating the viscosity of the decompression model. Let's use the 6 weight percent model as it's closest to the real world scenario. Let's use the 6 weight percent model from Mount St. Helens and calculate the viscosity of the melt during decompression of that magma. Okay, hopefully that makes sense. So you're going to use the same function as above, same keyword arguments. You're just going to change what you're providing in terms of those keyword arguments in here.
Yeah, your future warning, Heather. Thanks so much for posting this. So basically these, Matt, can you mute? Because again, this is horrible feedback.
Yeah, one sec.
When you see these future warnings, basically, let me just share my screen so everyone can actually see what this is. This is basically saying in Pandas 3.0, the way I have done some of the math of this Giordano method is going to eventually stop working. Now, you can totally ignore these as users. And what you can also do is you can email me this because it's really helpful for me to know, because you're probably on a slightly different version of Pandas to me, and this is not flagged on my slightly older version. But yeah, when you see these future warnings, it's good to let the developers know you don't need to panic for now. It's a panic for us, because when Pandas 3.0 eventually, becomes the version everyone's using, this is going to stop working and we're going to have to fix it. So yeah, thanks for posting that, Heather.
Awesome, thanks.
My headphones fell apart, which wasn't ideal, so just trying to fix that. All right, have we got answers coming through? Yeah, so I guess I didn't ask you to post anything. So if that does if that does work, I believe you should be able to run the cell below to compare. Yeah, so I think one of the reasons this looks a bit odd is you're getting the double label, right? So the reason why is actually in Thermobar. I just noticed this a second ago. There's actually two columns for the log of the viscosity, and they're giving exactly the same values. So it's just plotting two lines on top of each other. So yeah, so Penny, you're muted, but
Use end melt.
yeah, so you can change this instead of using the
I'll
log
fix that.
melt, use end melt instead. So just change that to end melt. And then rather than plotting the log viscosity, it will just plot the viscosity in Pascal seconds. So I'll change that in here. So is anyone getting issues with the viscosity calculation? So what's happened here, Dawn, is the key is 4.0, not 4. So because it's a string variable rather than like a number, it cares about the precision of like it being a .0. And then secondly, where you're specifying temperature, it should be Helen's decompress H2O equals 4.0, and then you need to say all or conditions before temperature. So I will start to kind of fill in some of this myself so people can see what I'm talking about. So the liquid compositions, Helen's decompress, I'm going to use the 6 weight percent one for liquid. And then for temperature, Helen's decompress, make sure you use the same calculation, otherwise you'll get a mismatch in the length. Specify all data frame, temperature plus 273.5. There you go. And so you should now get viscosity popping out. And so down here, once again, if you decide to use the 4 weight percent or 2 weight percent or 8 weight percent water, you're going to have to quickly change over these values in here to make sure you're plotting against the same thing. But all this code is doing now is showing the viscosity. And I guess this is why let's change that label. So it's not showing the proper symbol, but the viscosity in Pascal seconds of the Mount St. Helens decompression model against that kilowatt decompression model, right? And you can see that especially as decompression proceeds, we end up several orders of magnitude higher viscosity in this dacite relative to the basalt that we're comparing it to. In sense. And Penny is just posting something that I had forgotten, but you can do this. You can do a naught.set.
I'll paste in what that looks like.
X scale log.
See, I guess I'd never checked the log viscosity because I always plot viscosity and then log it.
Okay. Yeah. So yeah, you can then set the X scale to a log scale in that way, and so you can see even initially we're what 1, 2 and a bit, 3 orders of magnitude higher viscosity for Mount St. Helens compared to Kilauea, and that difference just continues to increase as you move up.
Interesting. The ether works for me. That's weird. It's not working on your computer.
Oh, really?
Yeah.
Oh, I might have accidentally deleted. One sec. I deleted a. There we go.
There you go.
I deleted a. Yeah. So, are you strict when you're doing like print statements or string statements in Python? The dollar symbol indicates kind of like mathematical text. So the dollar symbols, if you surround something with the 2 dollar symbols, within that is going to be mathematical text, and this is where you can put the backslash and then a Greek letter name, or if you wanted to do like superscript subscripts, this is how you would do that as well.
So you can basically see that Mountain Helens is 4 orders of magnitude more viscous, and that difference gets even bigger as you ascend towards the surface. And then obviously it's got way more fluid volume, so it does make sense that it's pretty explosive as things go. Yeah, I'll paste in my answers.
I'll keep this screen up for a little bit so people can
I'll
see
paste these in so
the
you will have
code.
it as well.
And so, I mean, you can kind of see what we're doing down here is actually exactly the same as what we did before, but actually a slightly different way of doing it. So this is the fluid volume fraction. And so here I'm looking in the volume data frame for fluid, and I'm comparing it to the volume, the sum of the volume data frame, and the axis equals 1 is just saying sum every row. Okay. So this is another way to get the total volume of the system at each step of the model, because we're summing the volumes of all the different components in the system at every step. And it's important in this case that we do this and we don't just compare fluid to fluid plus liquid, because for this Mount St. Helens, at least, I believe we do have some crystallization occurring. We'll talk about this in a little bit, but there will be some crystallization of materials happening during the Mount St. Helens decompression.
Well, Matt, it's 10:45 now. Given that we want to give people a little break before we do Major Min, do you want to just quickly show them the solids that they can look at the plagias, and then they can run through part 3 in their own time, maybe, or just quickly go through it?
Yeah, sure. So I can quickly go through. That shouldn't have been there. Apologies for that. Yes, if I quickly do this as so this is running now the calculation with Mount St. Helens, but I'm going to use the measured water content because I'm not specifying water anywhere in here. Okay, but I'm going to run it at different CO2 contents and label it by CO2. Okay, so the same idea, but we're now varying the CO2. We're saying we measured water, but we don't know our true CO2. So let's vary the CO2 and see what happens. Okay, so I'm going to run that. We could do this plot here would be doing the same as above, plotting the fluid composition and the fluid volume fraction. But actually what's kind of more interesting is to go down here, and in here, I'm extracting the mass of the system and the mass of liquid against the total mass, the mass of fluid against the total mass. And I'm saying solids are 1 minus that mass of liquid and mass of fluid, essentially. So I'm not worrying about what the solids are at this point. I'm just going to plot what is the mass of these components. And so you can see that in terms of the system mass, the liquid, is decreasing very slightly as solids start to precipitate even from around 2000 bars. And actually that decrease in liquid, as the fluid exsolves from 2000 bars, but then a major decrease in the liquid mass fraction occurs as solids actually start to precipitate from the system in the final 500 bars of magma decompression. And so we can kind of look into what those solids are by looking at the mass data frame, right? So we have Helens decompressed CO2. We can look into, let's say, take a moderate CO2 version, around 200 ppm, and we'd look at mass G. And so we can see that actually it's mainly spinel, and predominantly in terms of the mass you're seeing, predominantly going to be plagioclase is the material that's kind of the solid material that's precipitating from that solution as we decompress towards the surface with a small amount of orthoperoxene in these final couple of steps. So that mass increase in solids is predominantly occurring through plagioclase crystallization during decompression. This isn't that much of a surprise. Plagioclase is typically, we believe, it's destabilized by high water content, and we're losing our water due to the decompression during degassing. And also because plagioclase has quite a large molar volume, it's typically more stable at lower pressures. So the plagioclase phase field expands at lower pressures. So as we move to lower pressures, we degas and we lower the pressure of the system, we increase the stability of plagioclase and leads to crystallization of plagioclase during that decompression-driven step. So I think that's probably enough for me to finish there. We can leave this notebook for you guys to run through and have a go at like doing these final few plots. And also we have the option of running isentropic decompression. So this is if your decompression is truly reversible. So this is holding the entropy of the system constant. There is also in the future going to be the possibility of rising isenthalpic decompression as an alternative as well, depending on what you want to do and what you think is the most accurate for your system. In terms of the initial stages of magma decompression in the lower crust, maybe isentropic is more appropriate, with isenthalpic maybe being more appropriate in the upper part of the crust. Or maybe it's something in between the two, and we don't really know. But yeah, I'll leave that there. Hopefully that's been useful. And we're going to take a 10-minute break. And when we come back at 11, we're going to talk a bit more about Mage Men. If there's any questions, feel free to unmute, post in Discord, all that good stuff.
I've also posted in the Ask for Help channel, there's a more detailed example of Mountain Helen's degassing on the Read the Docs with an associated YouTube video. It shows a little bit more to how to look into these plagioclase microlights, how to plot them, and then you could compare them to your measured microlights, for example. So if you want more degassing stuff, have a look at that example. Cool, see you all in 10 minutes.